Okay, Chapter 11, Liquids, Solids, and Intermolecular Forces. So this is a picture from the space station of an astronaut looking through a very large droplet of water. There we go.
The question is, if you get a cloth dripping wet without gravity and you wring it out, what's going to happen? What will happen to a wrung-out cloth? So, and had you used equipment that was here on board the space station, we might have the coolest washcloths ever here on the space station. I'm going to show you. Here's one of our washcloths.
Veins up here on his head.
And it's packed. It's put down into this little tiny hockey puck so that it saves space. But when you open up a hockey puck,
No, space and space.
and you pull out your washcloth, this is the one I'm going to use for the experiment today. And so when you open up your hockey puck and turn it into a washcloth, it was compressed in a great big vise. Okay, so here's my washcloth, like a magic trick. And now I'm going to get this soaking wet, and then we're going to see what will happen when we wring it out. Meredith and Kendra suggested that I dip this in a bag, but bags don't hold water in space, so instead I fill a water bag. This has drinking water in it. And I'm going to squirt a bunch of water into this washcloth. Okay, so here's a soaking wet washcloth. Get the microphone so you can hear me while I'm talking. And now let's start wringing it out. It's really wet. It's becoming a tube of water. The water's all over my hands. In fact, it rings out of the cloth into my hands. And if I let go of the cloth carefully, the water sort of has it stick to my hand. Okay, so the experiment worked beautifully. And the answer to the question is, the water squeezes out of the cloth, and then because of the surface tension of the water, it actually runs along the surface of the cloth and then up into my hand, almost like you had Jell-O on your hands or gel on your hand, and it'll just stay there. Wonderful moisturizer in my hands. And the cloth doesn't really unravel itself. It just stays there floating like a dog's chew toy, soaking wet. Great experiment, worked perfectly. Meredith and Kendra, congratulations, great idea.
Okay, I don't know about you, but I think that's pretty cool.
So is it because he's in space and his veins are all weird? But what is going on?
Enough with the veins.
It's just trippy. It looks like he's doing this all the time. Like
Well,
it's
he's
not-
5 months.
yeah, it does stuff to you, I guess. He's probably got his feet under a bar on the floor so that he's not floating around. So he's probably concentrating on doing all kinds of things at once. Well, the lack of gravity does have an effect on your body. Yeah, it definitely does. On all kinds of stuff. All kinds of stuff.
So you'd be hypertensive but be in space. Is the pressure decrease?
You guys are so great at tangents. So here's water in a zero gravity situation, and touching it with your finger, it causes the water to deform and pull over onto your finger. We don't see things like this happen on Earth because the gravity's pulling the water down. So if you get droplets of water, like here's a little piece of water that came off, if you get that back over close to this, it'll stick together again. It'll glob together. Initially, this would be kind of a vibrating jello-looking thing, kind of oddly shaped. But if you don't disturb it, it will settle down and make a perfect sphere. And it does that because the water molecules are attracted to each other much like magnets are. And so they clump together, and they want to maximize their interactions with each other and minimize the surface area. And so that's why it always forms a sphere. So what is it that causes the water molecules to be attracted to each other? These are called intermolecular forces. They're forces between, that's what inter means, forces between molecules. And they exist between all atoms and molecules. They are significant only at very short distances. And they are responsible for the very existence of liquids and solids. Without intermolecular forces, there wouldn't be liquids and solids. So they are also essential for physiological processes like DNA replication depends on intermolecular forces, all kinds of things. These are very, very important part of everything. So we're talking about states of matter. The state of matter is going to depend on the relative strength of those intermolecular forces to the thermal energy. So I think of intermolecular forces as being a little bit like Velcro, or you could call it stick-togetherness. You know, how sticky are these things? If they're very sticky, it's going to take a lot more energy to pull them away from each other. If they're not very sticky, they'll just slide around, okay? When you increase the thermal energy, that's increasing the temperature, the particles are moving faster, and so they are more able to get away from the stickiness. So let's review. Oh, this is a new section. I'll stop here.